I was like, no. When I looked at the stream, I realized that like half of the stream was completely gone, and it must have been when I closed the YouTube window that it automatically just stopped. Something that I showed in the second part of the stream, which I think just gone completely missing, is how to transfer that discrete system into C code, which is also very useful for doing unit testing or doing any kind of simulation in C, where you need to where you cannot use the MATLAB functions, where you have to use just raw C code and just do the simulation, the dynamic simulation of the system. So you get an input, an activation signal, and the job of the simulation is to produce a reasonable response, which is close to what the real system would do when subjected to the same input signal. And to do that, it's possible to just translate this system, which we have identified in the previous video, and just to translate this into a discrete model, the Z-domain model. And the reason for doing that is that it's very easy to convert a Z-domain model into a set of difference equations, which are then easily convertible to C code, as I've done here. So this is just a simple program that reads the CSV file and outputs the simulation done in C. Basically the same simulation that I do with LSIM here in the MATLAB code. I say MATLAB code, but in reality I'm just using GNU Octave, but I use MATLAB to refer to anything Octave does. And basically, so I take this step and implement it in C, and it looks like this. So the coefficients that we get when we convert this, the TF gives us the continuous time domain transfer function, and then I convert it using C to D from basically doing it the second. We first have a discrete model, but it's a state space model. Then I convert it into continuous model. Then I convert it back to a discrete model. So it's really a lot of steps that probably are not necessary even. But just so that just to show how to go from the continuous time transfer function to a discrete function, which can be simulated in C, I do it this way. So C to D gives me the GZ, and then I use TF data to extract the coefficients B and A. B is the numerator and A is the denominator coefficients. So B is the output, and A, or let's see. So B would be the input signal actually, in this case. So let's see here. If I just run the not validate, if I just run the view here, yeah. So I get the discrete coefficients, and since and A, the first coefficient in A is 0, and that corresponds to the current result of the difference equation. So as can be seen in the comment here, the comment here explains how these coefficients fit into the difference equation. So we can write it like this. We can write the B coefficients multiplied by the current input xn and the previous input xn minus 1. And we can write it as an equality where it equals the current output times 1 plus the previous output times the coefficient A, or the second element of the coefficient A. And if we solve this for yn, we get yn equals xn times b, and minus yn minus 1 times A. And we can then easily compile this difference equation in C code, and I do it this way. So I scan, I read the CSV file, which is the normalized CSV file, which I've interpolated using interp here. So I've stabilized the sample rate. Usually when you sample data, you get variable sample rate, and that kind of messes up the simulation. Like we can see what it looks like. For example, if I use the original file, which has a different sample rate, data CSV, and then I can just do like this, out, and I can validate this. So using the wrong sample rate creates results that do not correspond to the actual measured signal. And imagine that if you have a sample rate that is completely not constant, like sometimes you sample at 1 millisecond, sometimes it's 1.5 millisecond, which is quite common if you use a non-real-time system. And even in real-time system, there is small variation with the sample rate. So it's very useful to take the measured data that you get from the measurements, from the experiments, and then to resample this data using interp1 into a constant sample rate. This really improves system identification, and it gives better results overall. So I resample this data, and then I save this data using CSV write into data number 2 file, like this. And when I then run the simulation in C code, I get results that look like this. So this result, the simulated data in blue, is following the measured signal very precisely, very closely. So this is the response that is simulated using this difference equation, and the green signal is the signal that is measured, and this is using the identified model of this system. So with this Octave model identification, you can easily just go and simulate this model very easily, very simply in C code, and you get the same response. Very useful. So this is kind of the part that was missing from the previous video. Really annoying that when I closed the window, it just totally it stopped recording. So I hope you learned something, and you can see the code clearly out on the screen right now. Just make sure that you're watching this in HD, yeah, and then you can use this. Happy using of system identification in your code. Hope you learned something. Bye.